Hello, everyone. Welcome to the Topological Matter seminar at CMSA. Today, we are very delighted to have Tat Lam from MIT to talk about dipolar SPT. Yeah, please take a start.
Okay, great. So first of all, I would like to thank everyone for coming. And before I start, there are two things. So one is I changed the title at the last minute. So the title before was Dipolar and Modulated SPT. But when I prepared for the talk, I realized that I probably won't be able to cover both topics. So instead, this talk will be just focusing on dipolar SPT. And if time permitted, I will make some comments about modulated SPT towards the end. And the second thing is that I'm currently in Asia, so it's a bit late here, so I'll be a bit slow. And if there's anything that's not clear, just please interrupt the talk and then ask questions. Okay, so with all this, let me start. So the talk today is about dipolar symmetry protected topological phases, or in short, dipolar SPT. And this is based on two works. So the first one is done in collaborations with Zhonghun Han, Ethan Lake, Ruben Barrozen, and Igio. And the second one is my single author work, which hopefully will appear this month. So let me begin with some general motivations and introductions. So as we all know and appreciate now that symmetry plays a vital role in the study of quantum matter and quantum dynamics. And in this talk, I would like to focus on a very particular kind of symmetry known as dipole symmetry. So what is dipole symmetry? Dipole symmetry is a symmetry which has two sets of conserved charges. So the first one is just the ordinary conservations of a total charge. And the second one is a conservation of dipole moments. So despite having this additional simple innocent conservation law, there can be many interesting physics phenomena that arises. And in fact, experimentally, dipole symmetry has also been realized in a lab. And so, for example, one system that has dipole symmetry is to place an ultra-cold atom systems on some strongly tilted optical lattice. And such strongly tilted optical lattice will generate linear potentials. And so having a linear potentials, which is a dominant potentials, then by energy conservations, then effectively we will have dipole conserving properties. So this kind of systems has an emergent dipole symmetry. So let me say a little bit more about why dipole symmetry could lead to some interesting phenomena. And the intuition behind this is actually very simple. So this is about how dipole symmetries can restrict the mobility of certain particles. So let's imagine that we have some charged particles, okay? So a single charged particle, so its motions will be completely frozen by dipole symmetry. And the reason is very simple. It's just because if we have a particles sitting somewhere, and if we move its positions, it will change the dipole moment, right? But such process will violate the dipole symmetries. And because of this, the motion of a single particle is completely frozen. But on the other hand, we can imagine that we have some kind of dipole that are made of a positive charge and a negative charge separated by some positions. And such dipoles can move around freely because its motions will not change the dipole moment. So such kind of restricted mobility arising from dipole symmetries are essentially resembling the physics of fractons. So fractons is just some kind of particles which are completely immobile. And here we see that dipole symmetries can lead to physics of fractons. But in addition to physics of fractons, it's not hard to imagine that dipole symmetry can also lead to interesting quantum dynamics. So for example, it can lead to anomalous hydrodynamics with very slow diffusion property. And it can also lead to breaking of agordicities and also non-thermalizations. But most of these discussions are through the lens of quantum dynamics. But on the other hand, it's also interesting to study quantum matters or quantum systems with dipole symmetries. So there can be interesting quantum phases if we just look at the systems with dipole symmetries. So in this talk, I'll just sort of follow this line of studying dipole systems, studying phases with dipole symmetries, and I will focus on just possibly the simplest phases of matter. So these are gap phases, and which I'll call them the dipolar symmetry protected topological phases. So what is a symmetry protected topological phases, or in short, SPD phase? So SPD phase are essentially phases, distinct phases that are gapped, short-range entangled, and also they're symmetric respect to certain global symmetry G. And this faces as a property that if we impose a symmetry throughout the phase diagrams, then all these phases are not connected to each other. So there's some phase there are phase transition that separates them. But on the other hand, if we allow deformations that violates the symmetries, then all of these phases will be connected. And such phases are called symmetry protected topological phases. And they're probably some of the simplest phases that one can ever think about. And one key characteristic of SPT phase is that the boundary will support some non-trivial degrees of freedoms and because of anomaly flow. So the goal of this talk is that I will discuss generalizations of symmetry protected topological phases to incorporate dipole symmetries. And the plan is that I'll first construct some explicit examples or explicit Hamiltonians that have non-trivial dipolar symmetry, dipolar SPT order. And I'll follow the idea of decorated domain wall constructions. Then I'll classify them using MPS states or matrix product states. And then I'll construct the response field theory. And it turns out this kind of response field theories are given by some kind of twisted finite tensor gauge theories. And towards the end, if time permitted, I'll comment on some general aspects about modulated SPT. Okay, so let me talk about the decorated domain wall constructions. So our goal is to construct some kind of Hamiltonians with dipolar SPT order, but it's generally very hard. So we will just follow the lesson that we learned from ordinary SPTs. So for ordinary SPT, the picture of decorated domain wall is extremely useful. So let me just demonstrate it in one example, and then we'll generalize it to dipolar SPT. So the example we'll consider is a famous example that is called the ZN cluster model. And so ZN cluster model is the model that defines some ZN spin chain with this Hamiltonians. So don't worry about the Hamiltonian at this moment. It's some Hamiltonians, and I will explain more about this. So it turns out that secretly this model defines a ZN times ZN SPT. So what are the two ZN symmetries? So these two ZN symmetries are symmetries that acts on the even sides and symmetry that acts on the odd sides. Oh, by the way, can you see my cursor just to make sure?
Yes, it's good.
Okay, good, thanks. Okay, so so there are these two symmetries, and another property of this Hamiltonian is that this is a stabilizer Hamiltonian in the sense that every term in the Hamiltonian commutes with each other. So that's actually very important because there are precisely there are precisely one stabilizer term for each side. So that means that the number of constraints is the same as the number of degrees of freedoms. So this tells us that the ground state is unique, just because all of these constraints are commuting with each other, and also because these are stabilizer Hamiltonians, so the Hamiltonians will also be gapped. So this matches with all expectations of an SPT. So in fact, this Hamiltonians, this very simple Hamiltonians can be understood using the picture of decorated domain walls. So the idea is the following. So let's first consider a spin chain, okay? And then we consider some domain walls. And remember that we have two symmetries. One symmetry is acting on the odd sides, and the other symmetry is acting on even sides. So let's consider a domain walls on even sides. So domain wall has a property that on the left side of the domain walls, all of the spins are pointing in some directions. And on the right side of the domain wall, all of the spins are pointing at some other directions, okay? So this is the domain wall configurations. So, but if we have a domain walls, one way to measure the domain walls, we want to use some operators to detect this domain walls. So this is made of Z and Z daggers separated by neighboring sites. And so a domain wall operator, if we place it at some places that are away from the domain wall, then this will be identity. But if we place this operator at the middle of the domain wall, then we see that this will get non-zero expectation values. So this operator is precisely operators that would measure where the domain wall is. So what's next is that we would like to decorate this domain walls with some kind of charge. And we'll decorate it with the charge of the other symmetries. So that means that we'll add an operator X, which is the building blocks of the charge on the odd sides, okay? So by adding this charge, then this tells us that we will bind some kind of, will bind the spins, certain spin configurations with the domain wall configurations. So away from the domain walls, all of the spins are pointing in the right directions. But on the domain walls, because of this kind of operators, then for this operator to be 1, then this a spin on the even side has to be pointing in the left directions. So this tells us that the spin on the on the odd sides is constrained fixed by the configurations of the spin on the even side, or fixed by the domain wall configurations. So it turns out that this kind of decorated domain wall operators, if we proliferate them, then this will give us some kind of SPT. And the reason is very simple, is because the ground state that constructed by condensing decorated domain walls will automatically preserve both symmetries. So for one symmetry, it will be preserved because we are condensing domain walls, and this will restore the symmetry. And for the other symmetries, that is because we are condensing decorated domain walls. So this will not create any long-range order, but instead it will create some long-range string orders, which is precisely the signature of an SPD phase. Okay, so here is just to review how an ordinary SPD can be constructed using the idea of decorated domain walls. So I'm going to generalize this to dipolar symmetries, to dipole symmetries. So the dipole symmetry that I will be considering turns out to be discrete dipole symmetries rather than the U1 dipole symmetry discussed in the introductions. So I will consider a dipole symmetry on Zn spin chains. So this is a Zn dipole symmetry, which consists of 2 symmetry generators. So the first one is a charge operator, which are simply made of products of axes. So this is a uniform operators, just products of axes at every side. And we also have dipole operators, which are made of product of axes to the power of its positions. So this is not the uniform operators. So the form of the operator will vary as we go from sides to sides. So these are the 2 operators that defines the dipole symmetries. And one key property of dipole symmetry is that the symmetry generator of dipole symmetry do not commute with lattice translations. In particular, if we look at how translation acts on the dipole operators, so dipole operator will not be invariant under the translations. Instead, the translations will, when it acts on dipole operators, it will generate a charge operator. So one can take this equations, namely the algebra involving the symmetry generators and the lattice translations as abstract definitions of dipole symmetry. Okay, so this is dipole symmetry that I would like to talk about, and I would like to construct some kind of Hamiltonian, so SPT orders with this dipole symmetries. Okay, so these are the 2 symmetries, and following the idea of decorated domain walls, we would like to first look at some kind of domain walls for dipole symmetries. So a criterion of a domain wall operator for dipole symmetry is that it should commute with both symmetry operators UQ and UD, but it should not commute with operators if we truncate them. So if we truncate the operator UQ, let's say on some finite interval, then the domain wall operator should not commute with such operators at the edges, because precisely if we act this operator on the states, this will create domain walls at the edges. So the domain wall operator could not commute with this kind of UQ operators defined on finite interval. Especially it should not commute with it at the edges. And such kind of domain wall operator is easy to construct. They're essentially given by a three-side terms made of a z and z dagger square and then z. So this is our domain wall operator. And so what we'll do is that we'll decorate this domain wall operators and then proliferate them. So by decorating them, we'll add a charge xi to this a charge x to this domain wall operators. So this is our decorated domain walls, and then it turns out that this kind of decorated domain wall operators defines stabilizer Hamiltonians. So a decorated domain walls at one side will commute with decorated domain walls at every other sides. And it's easy to check that the ground state of this Hamiltonian is unique and it's symmetric and short-range entangled. So this agrees with all of the property that we expect from dipolar SPT. But to really argue that this is a non-trivial dipolar SPT compared to the trivial product states, one way to argue that is to look for a protected edge mode. So we'll place this Hamiltonians on an open chain, and then we will ask whether there are protected edge modes localized on the edges. So So first of all, the ground states on this open chains will be stabilized by the decorated domain wall operators. So we can show that because of this stabilization properties, the symmetry generators, for example, the charge operators, in fact, factorizes into edge operators. So the idea is very simple. So this is our open chain, and then this is our symmetry operator, our charge operators that acts on the open chain. Okay. So if we focus only on the ground states, then this decorated domain wall operator AI will act as an identity. So that means that we can multiply AI dagger at the every sites from the second to the second last sites. Okay, so we'll do this for all of the sites from the second to the second last sites. And if we do this, then we see that all of the Z and Z dagger will just cancel out, right, in the bulk of the chains. And the X daggers will cancel out with the original symmetry generators. So what's left behind are the axis that acts on the first side, and the Z dagger that also acts on the first side, and also the Z acts on the second side. So similarly, there are some operators that are left behind on the right side. So at the end, the charge symmetry operators, we can just, when we focus on the ground space, and then it's equivalent to products of two edge operators, which are called LQ and RQ. So using a similar reasoning, one can also show that the dipole operator, in fact, also factorizes into edge operators localized on the left edge and the edge operator localized on the right edge. And the operator that we need to consider is this kind of products of AI to the power I. And then we take products of them from the second size to the second last size. And using this kind of operators, we can show that the dipole operator, in fact, factorizes into some edge operators. So now these edge operators are really the hero of the game, because as the edge operators are very far from each other, so and we know that UQ is a symmetry of the Hamiltonians, then these edge operators themselves has to be independently symmetries of the Hamiltonians. Okay. And furthermore, we can check that this edge operator obey some non-trivial algebra. So for example, the operator on the left-hand side, LQ and LD, they actually don't commute. And their commutations will generate a phase omega. So omega is an nth root of unity. And similarly, on the right-hand side, RQ and RD don't commute, and their commutations relations will generate an opposite phase. Okay, so because of this non-trivial commutation relations, then the edge modes, there must be some non-trivial edge modes to be consistent with such commutation relations. And for example, on the left-hand side, there should be unprotected edge modes. And this unprotected edge modes are transforming in the projective representations of this symmetry LQ and LD. So similarly, on the right-hand side, there should also be a number of protected edge modes. So here we see that just by analyzing the symmetries, we can argue that there must be some protected edge modes localized on the left and right edge of the open chain. So this indeed tells us that the model that we constructed must possess some kind of non-trivial dipolar SPT order. So this is one way to detect a dipolar SPT order. So there's also other ways to detect dipolar SPT order. In particular, we can also detect them on an infinite chain or a closed chain. We don't have to place them on an open chain. So on an infinite chain or a closed chain, one way to detect a dipolar SPT order is to look for something called string order parameter. So what is string order parameter? So a string order parameter is some operators that are made of a string of symmetry generators. Okay. And then we address the symmetry generators by some local operators at the end. And this string order parameter has a property that they will have zero expectation value in the trivial product states, but then they will acquire non-zero expectation value in the ground state of a dipolar SPT. So here are two examples of a symmetry of a string order parameter. So the first one is a string order parameter made of a patch of charge operators. So this is a patch of charge operators. And then to make it a string order parameters, we'll address it with some dipole operators on the two sides. So this will define a string order parameter. Similarly, we can look at a patch of dipole operators. And then we can address it with some charge operator at the endpoints. And this will define some string order parameter for the dipole symmetry. So using these two string order parameters, we can in fact track some phase transitions between the dipolar SPTs and the trivial phase. So as a simple example, let's just consider adding a Zeeman like terms into Hamiltonians. So this kind of terms are Zeeman type terms. So when lambda is very, very big, then the Hamiltonian is dominated by this kind of Hamiltonians. And the corresponding ground states are just product states. But when lambda equals to 0, then the Hamiltonian is dominated by the dipolar SPT Hamiltonians, and the ground state is in a non-trivial dipolar SPT order. So it turns out that this Hamiltonian enjoys some kind of duality that pins the phase transition to be lambda equals to 0.5. So now if we tune lambda from 0 to 1, we can track how the string order behaves. So in fact, we see that the string orders will go from a non-zero expectation values to some zero expectation values. And especially when it crosses 0.5, there's a phase transitions where the string order parameter in fact vanishes. So other than string order parameters, there's another way to detect dipolar SPT using entanglement spectrum. So what is entanglement spectrums? So entanglement spectrums are spectrum of the reduced density matrix when we chop the systems into two, okay? And a key property of a dipolar SPT is that the entanglement spectrum of a dipolar SPT has to be at least n-fold degenerate. But this is to be contrasted with the entanglement spectrum of a trivial phase. So here's an example of the entanglement spectrums as we tune the parameter lambda. And here I set the n, the n of the Zn spin to be 3. So the phase transition is expected to be at 0.5. So on the left-hand side of the phase transition, we see that every eigenvalues has a threefold degeneracy. So this is consistent with the dipolar SPT order. But on the right-hand side of the phase transitions, we see that the eigenvalues can be one-fold degenerate, or two-fold degenerate, or four-fold degenerate. So there's no protected degeneracies on the right-hand side. So this tells us that really there's a phase transition as we go from the lambda equals to 0 and to lambda equals to 1. Okay, so let me summarize what we have discussed so far. So far we have constructed Hamiltonians using decorated domain walls. And this Hamiltonians has a property that it is a stabilizer Hamiltonian. And we argue that it has non-trivial dipolar SPT order. And the reason why it has non-trivial dipolar SPT order is that if we put it on open chain, it will lead to n-fold protected ground state degeneracy per edge. And if we place it on infinite chain or a closed chain, we can in fact detect this using string order parameters. So the ground state of this Hamiltonians possess non-trivial string order parameters. And also the ground state has non-trivial degeneracies in the entanglement spectrum. So far it seems like a very consistent story, but there's actually a subtlety that I gloss over. So there's a subtlety that concerns about dipole symmetries on a closed chain. So far, most of my discussions are either on infinite chains or on open chains, and I didn't say too much about closed chains. So let's study what happens on the symmetry operators, in particular dipole symmetry operators on closed chain. So first of all, on open chain, the dipole operator is essentially a truncations of these operators, right? So it's a product of x1 to the power to x to the power l to the power l, xl to the power l. And this truncated operators defines or generates a Zn symmetry. But now let's consider what happens on the open chain. So, on a closed chain. So on a closed chain, this operators turns out it's not compatible with the periodic boundary conditions in general. And the reason is very simple, because on periodic boundary conditions, the operator x1 should be the same as the operator xl plus 1, right? And that means that this operator is well defined only if the power of x1 and the power of xl plus 1 are consistent with each other. And this is possible only if x to the power l is 1. And this is possible only if the length of the chain L is divisible by n. So that means that on closed chains in general, unless L is divisible by n, this operator UD is gone. It's not a well-defined operator. But even though UD is not a well-defined operator, we can consider some power of UD. So for example, we can raise UD to a power of n over k, where k is given by GCD of n comma L. So this operator is a minimal operator that is well-defined. And the reason is very simple. It's just if we consider x to the power L times n over k, this is always identity. So this is guaranteed to be identity. So that's why this operator is always well-defined on a closed chain. And this well-defined operator turns out to only generates a zk symmetry instead of a zn symmetry. So here we see that the zn symmetry of the dipole generators is in fact broken to zk by the periodic boundary conditions. And here we see a phenomenon that the symmetry, the form of the symmetry, the group of symmetries is actually sensitive to the length of the spin chain. So this is an example of UVR mixing that the symmetries or some certain properties of the infrared depends very sensitively on the short distance details. But this actually poses some kind of puzzle because we can consider the most extreme case where we set k equals to 1. So this is also the case where L and N are coprime, okay? So in this case, the dipole part of the dipole symmetry is completely gone and it's completely broken. But nevertheless, we expect that the SPT order should still make sense because the SPT order shouldn't depend too much on the boundary conditions, right? But then this poses a kind of sort of a puzzle that how should we make sense? How do we make sense of this dipolar SPT on periodic chain? So to answer this, let's first go back to the root and let's try to understand why the symmetry is gone. So the symmetry is gone in a very mild way in some sense. So the dipole generators, in fact, almost commute with the Hamiltonians, but except at one specific locations. So let's consider a dipole generator, which is defined as follows. So this is operators that is product of xi to the power I, and then we take the I to be from x naught to x naught plus L minus 1. Okay. So this is an operator that is defined depends on this operator depends on the value of x naught. So one can think of this operator as the truncations of the dipole generators on a closed chain. So if we plot the exponent of these operators as we vary on the chain, then the exponent is essentially a linear functions on the chain, right? And as a linear functions, it will always commute with the Hamiltonian. But the problem is that when we go around the spin chain, it's possible that this linear functions doesn't exactly come back to itself modulo n. And if it doesn't come back to itself modulo n, then this creates some kind of singularity. And this singularity is what tells us that this operator will not commute with the Hamiltonians. And precisely because of this singularity, the dipole generators will not commute with the Hamiltonian. But this non-commutation is in fact very mild. It's only occur at this specific locations. So from here, we see that this operator that I defined here seems to be a symmetry for any local patch. But there seems to be an obstructions to lift it to be a global symmetry for the full Hamiltonians defined globally, okay? And this kind of a phenomenon is in fact very much similar to fiber bundle. So it's similar to fiber bundle in the sense that the fiber bundle is something that is well-defined at every patch, and then we allow some kind of transition functions as we go from patch to patch. But then there could be some obstructions to define some kind of global sections of the fiber bundle as we go around the systems. So this suggests that maybe we can formulate this kind of dipole symmetry as certain kind of bundle symmetry. And if that's the case, then this kind of dipolar SPT can be viewed as some kind of SPT protected by bundle symmetry. So let me really just demonstrate it explicitly in this dipole symmetry case. So let's just consider our closed chain with periodic boundary conditions. So we will cover this chain by collections of overlapping patches denoted by A alpha. And on every patch of A alpha, we have some kind of operator, dipole operator, D alpha. So this kind of D alpha are operators that are like xi to the power I, and we allowed ourselves to add some freedoms in exponent, which depends on which patch we are on. And this freedom, the x alpha, varies as we go from patch to patch. Okay, so this is what happens on every patch. That there are some dipole operators, And notice that this patch, they are open patches. They don't wrap around the whole spin chain. And as we go from patch to patch on the overlapping regions of these patches, we allow some kind of transition functions. So for example, on a patch on overlapping regions between d alpha and d beta, the transition functions between the operator d alpha and d beta is given by xi to the power of x to the power of x alpha minus x beta. So we see that the exponent doesn't depend on the positions, right? So this is essentially an operator that is like a patch of the charge operator defined before. So here we see that on every patch, we have some kind of dipole operator. And on the overlapping regions, the dipole operators are glued, or they have transition functions. They are glued by charge operators. So this defines the dipole bundle symmetry for us. And we will say that a local Hamiltonian is symmetric with respect to this dipole symmetry if the Hamiltonian supported on every patch commutes with the corresponding dipole operator. And the direct consequence of this is that at the overlapping region, because the Hamiltonians that truncated within that regions commute with both d alpha and d beta, then it will commute also with the transition function, namely the charge operators. And now we can ask what happens about the symmetry operators that we defined before. What happens to the symmetry operator that defined globally? So here we have this kind of symmetry operators that are defined on patches. But if we want some actual symmetry or some genuine symmetry of the full Hamiltonians, then we want some symmetry operator that are defined on the whole spin chain, right? And for such kind of operator that to be defined on the whole spin chains, we want to lift this symmetry bundles into some operators that are defined on the whole spin chains with transition functions all equals to the identity operators. And this is essentially a mathematical question of whether such kind of bundle emits global sections. So in short, we have this kind of dipole bundles, and the global symmetries of the genuine global symmetry of the full Hamiltonians is really the global sections of this kind of dipole bundles. So now, using this dipole symmetries, we can rephrase the dipole symmetries. Using this kind of bundle symmetries, we can reformulate this dipole symmetries on the open chain, on a closed chain. And now we can really make sense of the dipole SPT now, because even though the genuine global symmetry of the full system is gone or is broken, this kind of bundle symmetry are still present. So we can think of the dipole SPT as some kind of SPT protected by this kind of bundle symmetry. Okay, so is there any question at this point? Just it's somewhat complicated or subtle. Just want to make sure that everyone is on the same page. Okay, it seems like there's no questions. So let me move on. So far I gave you one example of dipole SPT, but then one can ask, can there be more example of ZN dipole SPT? So in fact, the answer is yes. There's in fact a ZN class of dipole SPT, and they are parameterized by a variable, a ZN variable eta. And so the Hamiltonian of this kind of ZN dipole SPT are essentially given by the operator xi dressed with the domain wall operator raised to some power eta. And such if we place such Hamiltonians on an open chain, then we can see that the symmetry will fractionalize on the edges, and the fractionalizations will depend on eta. And this kind of algebras that we obtained on the edges will tell us that there are some protected edge degeneracy, and the number of protected degeneracies will depend on eta. So here we see that there's in fact a ZN class of, at least a ZN class of ZN dipole SPT. But then it's natural to ask, is this really the complete list of ZN dipole SPT? And this now goes into really a questions of classifications. What is the complete classifications of ZN dipole SPT? But before I jump into the classifications, let me stay with this constructive approach a bit longer. Let's try to generalize the decorated domain wall constructions to Zn times Zm dipole SPT. And in this case, there will be new features. So following the same logic as before, we want to construct some kind of stabilizer Hamiltonians with decorated domain walls. So we have domain wall operators that are made of this kind of three-side Hamiltonians. And we have domain wall operators for the Zn symmetry and also a domain wall operator for Zm symmetry. So this kind of Zn dipolar SPT are defined on some spin chains, and on the spin chains, at each side of spin chains, there's a Zn spin and a Zm spin, okay? And then for the Zn spin, I will denote the operators by X and Z. And for the Zm spin, the corresponding operators will denote with tilted operators. So that that are given by X tilted operator and Z tilted operator. So it's easy to construct the decorated domain walls by decorating this operator X with the domain wall operators. And we allowed ourselves to add some powers in the decorations. So they are given by eta, lambda, eta tilde, and lambda tilde. But it turns out that for this Hamiltonian to be a stabilizer Hamiltonian, which is crucial for the Hamiltonian to define an SPT, the decorations parameter lambda and lambda tilde has to be correlated with each other. And so the Hamiltonian turns out to be commuting Hamiltonians only if lambda is given by m times zeta over k, and lambda tilde equals to n times zeta over k, where k is given by GCD of n comma n. Okay, so this suggests that the actual Hamiltonians, stabilizer Hamiltonians, are actually parameterized by only 3 parameters. So one of them is the eta parameter, which is a Zn parameter, because if we raise the domain wall operator to Zn power, this actually vanishes. Okay, it becomes an identity operator. So similarly, eta prime will parameterize a Zm group, and the zeta parameter takes value in Zk. So this seems to suggest a Zn times Zm times Zk classifications for dipolar SPT. But again, this raises the question, is this really the complete list? So to answer this, let's study what happens to this dipolar SPT when we place it on an open chain. Okay, so on an open chain, the charge and dipole operators can fractionalize on edges. So the charge operators and dipole operators are given by Q and D, which comes from the first set of Zn symmetry. And we also have Q tilde and D tilde operators given by the Zm dipole symmetry. Okay, so on the edges, the operator Q and D, in fact, can be non-commutative. And their commutations are governed by some parameter, are governed by the parameter eta. So similarly, Q tilde and D tilde can also be non-commutative, and with a phase that is given by eta tilde. And the parameter zeta actually enters into the commutation relations between Q and D tilde and Q tilde and D. So it turns out that Q and D tilde, their commutations are given by the phase exponential 2 pi I zeta over k. And this is precisely the same phase that will also enter into the commutation relations between Q tilde and D. So this is all the possible fractionalizations patterns that can exist on such kind of dipolar SPT. And it's easy to observe that so far, all of the fractionalization patterns are only between the charge operator and some dipole operators. Then it's natural to ask, is it possible that the charge operator themselves or the dipole operator themselves can be non-commutative on the edges? Namely, we want some kind of non-commutation relations between Q and Q tilde or D and D tilde. So the answer turns out to be yes, at least for the dipole operator. So for the dipole operator to be non-commutative at the edges, we need to look for something beyond decorated domain walls for just using dipole symmetry. We need to look for quadrupole domain wall operators. So quadrupole symmetry has an additional operator other than the 2 operators that we discussed before, the charge operator and dipole operator. So additional operator is what's called quadrupole operators, and it's essentially given by xi to the power of I squared. Okay, so a quadrupole domain wall operator has a property that it should commute with the quadrupole operators, but it should not commute with the edge of a quadrupole operator if it defines on a patch. And this is precisely the domain wall operator that does the job. So now with this domain wall operators, we can decorate it with some charge, and then this will lead us to the following stabilizer Hamiltonian, which are parameterized by xi. And this xi is a zk variable. So it turns out that this model is circularly is a quadrupole SPT, not just a dipolar SPT. So it has a Zn times Zm quadrupole symmetry. But in the talk, I will just focus on the dipole symmetries. I will neglect the quadrupole operators and think of this as a Zn times Zn dipolar SPT. Okay, so if we study this Zn times Zn dipolar SPT and on an open chain, we learned that in fact the dipole operator D and D total do not commute with each other, and their non-commutations is given by a phase that is governed by cosine. Okay. And this tells us that, in fact, on top of the previous classifications, there's in fact at least another ZK class of dipolar SPTs, which has dipole fractionalizations on the edges. But again, we go back to old questions. Is it really the complete list of Zn times Zn dipolar SPT? And in particular, can there be dipolar SPT with charge-charge fractionalizations? So to answer this kind of questions, we really need to go into the questions of classifications. So to classify this kind of SPT or dipolar SPTs, we will need to work in some kind of framework. And the framework that we will work with is matrix product states. So what are the matrix product states, or in short, MPS? So MPS are states that are built from contracting the MPS tensors, okay? So MPS tensors, as I've drawn here, is the tensors with 3 legs. So it has one physical legs with indices that are given by the indices of the physical Hilbert space, and it also has 2 virtual legs, okay? And here, when I draw a picture like this with some bounds connecting 2 tensors, what I mean is that the indices of these 2 tensors will be contracted. So MPS states are given by superpositions of all possible configurations of the physical on a physical indices, and then the weight of this states are given by the contractions of this MPS tensors, like this. So this defines the MPS states. So essentially, MPS states are controlled by this MPS tensor. And the reason why we can work with the MPS states to classify dipolar SPT is very simple. It's because there's a theorem that states that every ground state of every one-dimensional gap Hamiltonians can be well approximated by MPS. In particular, we can make the approximation better and better by increasing the bound dimensions, namely the number of indices that run in the virtual bound at the virtual level. Okay, so in fact, using this MPS, it was shown that it was used to classify the ordinary SPT in the past. So I'm going to review this quickly here, and then I'm going to generalize it to dipolar SPT. So to classify ordinary SPTs, we need to use a very important theorem. And this theorem says that if an MPS is symmetric with respect to global symmetry that are made of product of UG, namely this is a symmetry that is uniform, okay? Then it is if and only if the unitary operator UG can be pushed through the MPS tensors as follows. So we can push through the UG operators through MPS tensors and creating an operator VG and VG dagat at the virtual links that acts on the 2 sides of the MPS tensor. And here VG are some kind of unitary operators. So this is the theorems. And let me emphasize that this theorem only works if the symmetry QG is really a uniform symmetry that are really made of products of UGs at every site. In particular, it doesn't apply to dipole symmetries. So to prove this theorem is in general very hard. In general, takes some effort, but it's actually easy to verify that if the push-through property is true, then the MPS has to be symmetric. So the idea is very simple. Let's just push through the symmetry operators through this MPS states. So if we push through the operators using the push-through properties, then we get VG and VG daggers at the virtual bounds. And because VG are unitary operators, all these VGs will cancel out. And then we are just left behind the same MPS tensor, MPS states as before. Okay. So now to classify SPTs using this kind of MPS, we will need to place it on an open chain and look at the possible projective representations at the edges. So on an open chain, an MPS is not just specified by the MPS tensors, it's also specified by the boundary data. So boundary data involve 2 virtual boundary states, which are some vectors that take the dimensions of the the virtual bound dimensions. Okay. So this is the MPS state. In particular, the MPS tensors are sandwiched between two vectors, which defines the virtual boundary states. So now we can push through the symmetry operator through the MPS through this kind of MPS states using this push-through property we obtained before. So if we do this, we'll get a VG operator acting on the left virtual states and a VG dagger operator acting on the right virtual states. Okay, so this is our state after pushing the symmetry through. And it's important that the symmetry QG itself have to act linearly on the MPS states, but operator VG doesn't have to act linearly on the virtual state. In fact, they can act projectively with some phase that depends on G and H. And this phase will in fact cancel out if we study the fusions of two symmetry operators QG. And in fact, such kind of phase will not affect the linear actions of of the operator QG. Okay, so now the questions of classifying GSPT really just boils down to the classifications of projective representations of this kind of virtual operators. And the projective representations of a symmetry group G is known to be classified mathematically by a second group homology of this group G valued in U1. So this reproduces the famous classifications of an ordinary SPT with a symmetry G. Now I'm going to generalize this to dipolar SPT. So for dipolar SPT, in addition to the symmetry QG, which is a uniform symmetry, there are dipole operators, right? So dipole operators are products of UG to the power of its position. So now we can study what happens if we push this dipole operator through the MPS state. So if we push this dipole operator through MPS states, we can use the same push-through property as before, because remember that our state is also symmetric with respect to the ordinary symmetry. So the push-through property, if we apply it, then we'll get VG that acts on the virtual bounds. But now the VG will not cancel out. What happens is that we'll get VGs sandwiched between the MPS tensors. So it seems that the MPS is not symmetric with respect to DG. But now here comes with another theorem that we prove that an MPS is symmetric with respect to the DG operator if and only if the virtual operator VG can also be pushed through the MPS tensors as follows. So if we push the VG operator through the MPS tensors, we get the operator WG, which is a unitary operators, acting on both sides of the MPS tensors. Okay, so this theorem, again, takes some effort to prove, but it's easy to verify the other directions. Namely, if this property holds, then the MPS will be symmetric with respect to DG. So let's check it. Let's really verify these properties. So before we stop at this figure, when we push the operator DG through the MPS tensors and through MPS states, now we can apply this push-through property and then push all of the VG operators through the MPS tensors. Then we get something like this. We get some WG operators acting on the virtual bounds. But because WG are unitary operators, so they cancel out with each other, and then we were left behind with the same MPS state as before. So here we indeed verify that the push-through property of this VG operators implies that the MPS is symmetric with respect to the dipole operator. So now let's place the MPS on open chain and then study what are the possible projective representations are allowed at the edges. So we'll push this dipole operator through the MPS. And if we do this, we'll get a WG operator acting on the left virtual boundary states and a more complicated operators acting on the right virtual boundary states. So this operator involves WG dagger and also VGL dagger. So the reason why we get VGL dagger is because we are pushing UG to the power L, right? So when we push this through, we'll get the VG to the power L dagger. And then we get this WG dagger is because we are pushing some VGs that sandwich between this two MPS tensors through this tensors. So this is what happens if we push the dipole operator through. And in particular, it's important that we see that we get this VG operators with a very particular powers that depends on the length of the spin chance given by L. So precisely because of this this kind of unusual push-through properties, or with this power of L in the VG operators, well, we can show that the possible projective representations of the virtual operators are in fact constraints. So for now, I'm going to just restrict my attention to the case where the dipole symmetry is defined for some finite group G, a finite abelian group G. So G will be a finite abelian group. So in this case, all of the symmetry operators should just commute when they act on the MPS states. And for such kind of operators, because they are abelian, so if they are linear, if they act on linear representations, then the operator should commute. But if they are acting on projective representations, then the commutations could generate some kind of phase. So to parameterize the projective representations, they are parameterized essentially by the phase that will pop up from the commutations of the virtual operators. So in total, there are three kind of phases that could appear coming from the commutations of V, W, and V and W. And such kind of representations are classified by the second group homology on G times G. And the reason is very simple, is because the operator V generates a symmetry G, and then operator W also generates a symmetry G. So that's why the most general projective representations is given by the second group homology on G times G, valued in U1. Okay, so now we have this this kind of most general representations. We can ask, are they all allowed? Are they all compatible with dipolar SPT? So it turns out that it's not always the case. And the reason is following. So because we are considering finite abelian group, right? So, and we expect that the symmetry should act linearly on the state. So the operator QG and DH should just commute with each other. And so now let's check what happens if they commute. So if we act QG and DH on the MPS states, then what happens is that if we push DH through, we'll get this complicated operator acting on the right boundary states, like what I have written here, and also the boundary operator W acting on the left boundary state, like what I've written here. And if we further push Q operator through, then we get VG dagger and VG acting on two sides, of the boundary data. Okay, so this is operator. This is the state that we get. So now we can use the commutation relations of coming from the projective representations, and to exchange V and W's, and if we do that, we'll generate a phase. And the reason why I get this phase is because we are commuting VG dagger past VH to the power L dagger, and we commute that. If we could do these commutations, we'll generate a phase that is proportional to exponential I alpha. Okay, and then there's a proportionality constants given by L. So the state that we get at the end is essentially the state that obtained by first add QG on the MPS states, and then we add the dipole operator on MPS states. So here we see that the operator, the commutations of QG and DH, is not always, can generate some kind of phase, and this phase will depend on exponential I alpha. But we expect that QG and DH should commute with each other. So this tells us that exponential I alpha has to be 1. And in particular, it means that the operator VG had to always commute among themselves. And so that means that we should quotient out the projective representations of BG that are classified by the second group homology on G from the most general, the projective representations. So other than these constraints, we can obtain other constraints by looking at the commutational relationship between DG and DH. So from this commutational relationship, we learned that the phase exponential I gamma that pop up from the commutation between V and W, in fact, have to be symmetric between G and H. And this tells us that there's another quotient we need to do. And this quotient is also given by the second group homology of G. So in the end, the final result is that a G dipolar SPT with a finite abelian group G is classified by this quotient group. So it's classified by the second group homology on G times G over the second group cohomology of G to the power to the square. Okay, and for a finite abelian group that is made of product of a cyclic group, we can in fact compute this explicitly, and it's given by two kind of factors. So the first one is a product of Z and Ij. So Nij is given by GCD of Ni and Nj. And here the products, let me emphasize the products is from I less than equals to J. And there's also a second kind of factors that is also given by products of Z and Ij, but then this is only for I less than J. Okay, so it turns out that these two factors has their own physical meaning. So the first one turns out to be classifying all of the dipolar SPT that exhibit charge dipole symmetry fractionalizations at the edge, and the other one are classifying dipolar SPT with dipole SPT. And in fact, this agrees with the previous constructions that we constructed before. And in particular, there are no dipolar SPT that exhibit charge fractionalizations at the edges. Okay, so far I show the classifications, and in fact, this tells us that all of the Hamiltonians that we constructed through decorated domain walls before, in fact, are the complete list. They reproduces all of the Zn dipolar SPT and all of the Zn times Zn dipolar SPT. Okay, so this concludes the section about classifications. Now I'm going to move on to talk about response field theories. So now we would like to construct some kind of response field theories for dipolar SPTs. So to construct such kind of response field theory, we need to couple the symmetry to background gauge fields, right? But to motivate this kind of background gauge fields, let us first consider U1 dipole symmetry. So U1 dipole symmetry can be has a natural conservation equations, which is given by this. So the derivative of the charge density is not given by the derivative of some current, rather it's given by second spatial derivative of some current. So precisely because of this second spatial derivative, this kind of currents can give you two charges. One is the dipole charge, and the other is the usual ordinary charge. So because with this symmetry currents, we can couple them to background tensor gauge fields through this kind of couplings. So rho is coupled to background tensor gauge field AT, and J is coupled to a background tensor gauge field AXX. And for this kind of coupling to be gauge invariant, we need the background tensor gauge fields to obey some kind of non-standard background symmetry transformations. In particular, the tensor gauge fields AXX has to transform as a double derivative of alpha. Okay, so this is my background gauge fields. So it's not a standard tensor gauge fields, but rather some kind of tensor gauge fields. So this is a gauge field that a U1 symmetry should couple to, and for Zn dipole symmetry, then it should be coupled to a Zn version of the tensor gauge field. So a Zn tensor gauge field is very hard to deal with. So a natural way to deal with them is to embed them in U1. And but to embed them into U1, we need to introduce some kind of compact scalar phi as some kind of Lagrange multiplier. And what this Lagrange multiplier is doing is constraining the field strength of the tensor gauge fields to be 0. So this tells us that this tensor gauge fields are flat, and also that will constrain the holonomy of this U1 tensor gauge fields to be Zn. Okay, so this is the constraints that we need to put in to make a U1 gauge fields into a Zn gauge fields. So now for the most general dipolar SPT given by some finite abelian group G, the response field theory will take the following form. So we always have this kind of terms that tells us that the U1 gauge fields are constrained to be Z and I. And then on top of these, there are some functionals of the background gauge fields that we can add. And these functionals will depend on which dipolar SPT we are focusing on. And for this response field theory to describe a dipolar SPT, there are some criterion that we need them to satisfy. So the first criterion is that this response field theory has to be gauge invariant. It should be gauge invariant on a closed chain. And but on the other hand, on open chain, it can be non-gauge invariant. And the non-gauge invariance will be some kind of boundary terms, which will give rise to a norm inflow. So on top of this, we require that the coefficient that appears in this response field theories has to be quantized. And this is because we want to match it with the classifications of dipolar SPTs. And we know that dipolar SPTs are classified by discrete numbers, right? So that means the coefficient has to be quantized. So this kind of properties are essentially analogous to Digraph-Witten theories that we usually define for G gauge fields. But here, this is sort of a generalization of Digraph-Witten theories to finite tensor gauge fields. Okay, so now with this background gauge fields, we are now ready to construct the response field theory. So let's first consider charge dipole fractionalizations, like SPT with charge dipole fractionalizations. So the response field theories are given by this kind of terms that are made of products of AT and AXX. And then we are allowed to add some flavor indices, and we are allowed to contract different kind of different gauge fields from different flavor indices. And the contractions that we allowed are given by this kind of symmetric matrix Kij. Okay, and this Kij matrix has identifications given by Nij. And the reason is because this AT and AXX are ZNI gauge fields, right? So they're holomia constraints. And when Kij are exactly given by Nij, this part is precisely 2 pi times integer. So that's why, and this will not have any effect. So that's why Kij has this kind of identifications. Okay. So in fact, having this kind of terms, the Lagrangian in general will not be gauge invariant unless the compact scalar phi I that used to constrain the tensor gauge fields also transforms under gauge symmetries. And the way they transform under gauge symmetry is just through this kind of transformations, and which are controlled by Kij. And it's important that phi I, which is a compact scalar, and also alpha j is also a compact scalar. So since both of them are compact scalars, then the coefficient that can enters into the gauge transformations has to be integers. And this tells us that Kij are quantized to be integers. Okay. So this gives us a set of response field theories with charge dipole fractionalizations. And let's also consider what happens to SPTs with dipole fractionalizations. So for such kind of SPT, the response field theories are given by products of AXX and partial X of AT. Okay, and then we are allowed to contract again different flavor indices through some kind of matrix, and this matrix Gij has to be antisymmetric now for this term to be non-trivial. And again, we require that the compact scalar has to transform under the gauge symmetries for the actions to be gauge invariant. And the coefficient Gij is again quantized just because phi I and alpha I are compact scalars. So at the end, together we get two kind of response field theories. So one of them is parameterized by symmetric matrix, and the other is parameterized by antisymmetric matrix. And it turns out that it exactly matches or reproduces the classifications. So it is because a symmetric matrix, Kij, with coefficient identified up to Nij, are precisely parameterizing a group that is given by products of Z and Ij for I less than equals to J. So it's important that it's symmetric, so I has to be less than equals to J. So similarly, antisymmetric matrix parameterizes such group where I is less than J. Okay. So here we see that the response field theory that we obtained exactly matches or confirm the classification that we get from NPS. Okay, so this concludes my talk. So let me summarize what I have discussed so far. So I discussed SPTs protected by dipole symmetries. Okay, and then we construct families of stabilizer Hamiltonians with dipolar SPT orders by generalizing the idea of decorated domain walls to dipole symmetries. And using MPS, we classified all possible G-dipolar SPTs when G is a finite abelian group. And the classification is very simple. It's given by this quotient of a second group cohomology on G times G over a quotient over a second group cohomology of G. And in particular, we show that not every possible symmetry fractionalization pattern are allowed on the boundary of dipolar SPT. In particular, charge-charge fractionalizations are forbidden on the boundary of a Dipolar SPT. And we also construct the response field theory for Dipolar SPT, and they are given by some kind of twisted finite tensor gauge theories. And this finite tensor gauge theories exactly matches and reproduce the MPS classification. And also, we run into some puzzles of defining dipole symmetries on periodic chain. And one way to make sense of this kind of dipole symmetry is to think of them as some kind of bundle symmetries, which are defined by operators on various overlapping patches with transition functions. And as a result, if we want to think about the dipolar symmetry on periodic chains, one way to think about them is some SPT protected by some kind of bundle symmetries. So that's everything I want to say, and thank you very much.
Thank you, Hotan, for the very clear and nice talk. Is there any questions from the audience? So maybe let me start with some very basic questions. So for the periodic dipole SPT, so you mentioned the global dipole symmetry is not well defined except it's periodic. Is that so? Then in order to so this motivated you to define the dipole or the bundle symmetry. So you divide this space manifold into some patches and are you lost online?
Except that's right.
Yeah. So why you call it symmetry? Can you?
Oh, I'm still here. Can you hear me?
Yeah.
Oh, good. That's a good point. Okay, so let me go back to the. Give me a second. Let me go back to the definition of bundle symmetry. Okay. Sorry, I think I lost connection.
Yeah. No problem.
Let me join again. Okay, so let me come back to this. Yeah, that's a good point. So first of all, this is the definition. So sorry, this is what I mean by Hamiltonian symmetry with respect to dipole bundle symmetry. Okay, so what I mean is that a Hamiltonian, if it truncated into a specific patch, then this will commute with the corresponding operators. Okay, so that means that if we just focus on one patch, then the Hamiltonian restricted to that patch, sorry, the operator d alpha will be a symmetry of that Hamiltonian, of that truncated Hamiltonians. So that's why I call it a symmetry. But the problem is that we know that operator d alpha, even though it's a symmetry of that truncated Hamiltonian, it's actually not a symmetry of the full Hamiltonian, because the full Hamiltonians could have terms that crosses the patches, right? That, for example, there could be terms that have both supports on d alpha and d beta. Okay, and such kind of terms will not commute with d alpha. So d alpha is only a symmetry of the truncated Hamiltonians, but not a symmetry of the full Hamiltonians. Okay, and so if we want for traditional sense of symmetries, we want some operators that commutes with the full Hamiltonians. So that really requires not just the operator d alpha. We require d alpha to be defined everywhere with the trivial transition functions. Yeah. So that's what I mean. Yeah.
So usually when we so is there any analog of the bundle symmetry for the usual case like the magnetic monopole? Still we have a disconnected section patch set. Okay, never mind. If its connection is lost. Okay, is there any more questions from the audience?
Oh, like that. So the bundle that we get would be similar to the gauge bundle of around the magnetic monopole. So that will be very much similar. Like you can have non-trivial topology. Oh, sorry. You can't hear me, bro?
Oh yeah, I can. Yeah. So is there any more question from the audience?
Can you hear me?
Oh yes, I can, but the
Okay.
internet is not very smooth. Okay. So if there's no further question, let's thank Hoten again for the wonderful talk. Okay, thank you.